Ladies and gentlemen, we start the last lecture. And today, usually I start a lecture by summarizing what we did last time, but I won't. I will summarize what we did the whole semester. Okay? So, aim of today is to just go through the whole semester. So I printed out the table of contents, and I also thought and reordered some of the stuff so that we can present it all in one lecture. Let's see if we manage to do it. Of course, it will be short. But I think the main things that we learned will be summarized. So, as you remember, the thing that we looked at throughout this lecture is one optimization problem. So let me just state it. So this is the lecture summary. And we always looked at the problem which was just minimizing a function of x subject to some equality and inequality constraints. That was the general problem, and I recall chapters 1, 2, and 3 first. So that's what I want to summarize first. We call this thing an NLP, and the statement, how I wrote it here, is slightly incomplete, so we should also ideally give which space our variable lives in. So this is a clean statement of an NLP. You remember what was the feasible set? Very often we called it omega. It's a set of all x that satisfy the constraints. And then we also had definitions of a global and of a local optimizer, right? So I think the interesting thing, x is a global minimizer if and only if. What should hold? First of all, x should be a feasible point. And then for all x in the feasible set, the function value of fx should be bigger than f of x star. That's what a global minimizer is. And x star is a local minimizer. If and only if. What would hold here? If there exists some neighborhood. Actually, maybe I should first copy this thing. So it's the same. So x star element in omega. And there exists a neighborhood so that for all x which are in omega intersected with this neighborhood, you have that f of x is bigger than f of x star. These were the plain definitions, mathematical definitions. And we then went through a collection of problems. And I would like to summarize a few of the problem classes that we introduced. So the first one are LPs, linear programs. What are they? They are problems where f, g, and h are affine functions. An affine function, g of x, for example, is ax plus b. So that would be an affine function. And so if f, g, and h are affine, we speak of an LP. The constant term of f is usually omitted, but that doesn't make a difference here. QPs. So when do we have a QP? If g and h are affine, and f is linear quadratic. QPs can be convex or non-convex. LPs can be always only convex. So how do we define convex problems? And there were different definitions of them. Basically, the plain definition would be that f should be a convex function and omega a convex set. And if these two things are satisfied, then we would say this is a convex problem. Unfortunately, it's very difficult to find out if a set is convex or not. But there is a sufficient condition for omega being a convex set that we derived. And this condition was actually that the g is affine and that the minus h are convex functions. So for each component. Do you remember that? And usually if you have a convex optimization solver, you require that f is convex, g is affine, and minus h is convex. So when is a function convex? So that's also something we should keep in mind. F is convex if and only if. There are some conditions, and I will not keep the definition. I mean, you can have the definition and think about it. Also, what's the definition of a convex set? But the interesting thing, if f is twice differentiable, that's a detail I'll omit here, then it's convex if for all x the second derivative of f is a positive semi-definite matrix. So that's an interesting property because we can check it by computing. And why are we so interested in convex optimization? Because there is a theorem that says if the NLP is a convex problem, so if this is convex, that will imply what? That a local is also a global minimizer. So whenever you have found a point that satisfies these conditions, it is actually satisfying this condition as well. Extremely strong. I already called this thing an NLP, so what would be, what do we strictly call an NLP? So that is a problem where we would say that the functions f, g, and h have a certain property, and that is usually that they are differentiable, and most algorithms use actually twice differentiable. So they are C2 functions, twice differentiable functions. And that is, of course, the main topic of this lecture, right? So we didn't really cover in detail LP or QP algorithms. There is another class which we called integer programming, IP, which basically just adds an additional constraint, x element in Zn. So it's not in real numbers, but in Z, in integer numbers. Then we talk of integer programming. And that's what appears in logistics and so on. Scheduling. So it's a very important class, but not treated in this lecture, but we should know about it. And there exist good solvers for it. So this is the summary of the introduction. And now I would like to go to chapter 4 directly. And what we did in chapter 4 was we introduced the Lagrangian function. So the Lagrangian was this interesting object that, so that's chapter 4. The Lagrangian x lambda mu, we should always remember what it is. We needed it a lot, right? Also later. So this function. And we also defined a function that is, this is called the Lagrangian. These are the Lagrange multipliers. But we also defined the Lagrange dual function. And the Lagrange dual, we used the name Q, even though Q was doubly used sometimes as an index, I should say. But anyway, Q is a function of lambda and mu alone. And it is a function if you minimize the Lagrangian over x. So it's actually the infimum over all x in all real numbers over the Lagrangian. So that was an interesting function. There is a property of this dual, the Lagrange dual function is always a concave function, I think. Right, so we could actually show that this is a concave function in lambda and mu. And so it's an interesting problem to ask which would be the maximal Q. And so we know also it's an underestimator, and what we call the dual problem is something that is now maximizing this Lagrange dual function Q of lambda and mu over all lambda and mu in this suitable space, but subject to mu being positive. And there is, of course, something that we proved already, and we proved that this thing here, which we could call D star, the dual optimum, we could compare it with the primal optimum that I call P star. It's the value of this function. And then we have a theorem that says weak duality and that we have proven earlier, and that was actually that the D star is a lower bound of the P star, so it's an optimistic estimate. There's also strong duality, and that holds for convex problems. This is always, weak is always, and strong duality holds basically for convex problems. There are some exceptions where it also holds in addition in other cases, but the most important special case is convex problems where strong duality holds, and there the two things are the same, and a lot of positive properties follow from that. So, I thought it's maybe nice to also indicate which chapters in a book of Nosedal you could find information on these topics. So the Nosedal book, I just cited like this, Nosedal. And so if you just read chapter 1 in the Nosedal book, you would get a good overview of these topics. About this duality, you would probably look into chapter 12, 9, at least in the edition that I had. So there might be new editions with different counting. And that's for this blackboard, the summary of the first 4 chapters in 20 minutes. I will move it to the top and now go to my favorite big table. It's a table that summarizes all optimality conditions that we have covered in this course, and it will need, I would say, maybe the whole blackboard. So let's try to summarize the chapters which were on optimality conditions, and we distributed them throughout this lecture in 3 chapters. Let me just check it up. So it was chapter 5 and chapter 11 and chapter 13. 5, 11, and 13 was all about optimality conditions. And we started easy and make it more and more complicated. And of course, the easy cases are special cases, are the more complicated ones. But I like to make a table which starts, so to say, by having the unconstrained, having the equality constraint, and the inequality, the equality and inequality case. And of course, I could only state the last thing because it covers all the others. I could just say every unconstrained problem is a constrained problem without constraints, right? So, and then you just omit the things. But because that is a bit nasty, let's say, I want to start with the easier parts and then go on to the more complicated parts. So here we have just an F, here we have an F and a G, and here we have an F, a G, and an H. And things get more and more complicated the more constrained types we have. And so here I want to list the first order necessary conditions of optimality. And what do they state? Basically, they say X star is an optimizer. That implies something. And what it implies is what I will put into this table. So let's go through the first thing. So it implies that if we are at an unconstrained minimum, that the gradient of f at this point is 0. So that's the first order necessary condition for unconstrained. What does it imply for equality constraints? It implies that there exists a lambda of the appropriate space, so that the gradient of the Lagrangian with respect to, I call it lambda star, to x is equal to 0. And for completeness, we also state that it should be a feasible point. So these are the necessary optimality conditions for the equality constraint case. And I should say that here in this case we always assume LICQ. So I will not state the full theorems again, but for the constraint case, of course, we have to assume LICQ. How do they look for the equality and inequality constraint case? They are much more complicated again. So there exists a lambda star and a mu star so that the KKT conditions are satisfied. But what were the KKT conditions? They were, first of all, that the gradient of the Lagrangian with respect to x at this point is 0. Second, that the equalities at x star are satisfied. Third, that the inequalities are satisfied. And because I like to make it by indices, I directly use an index here and say I is going from 1 to q, and q is now not the same q as up there, just the index of the inequalities. And then there were more conditions, namely that the mu multipliers should also be positive for each component. And then also that the product of the two should be 0. So the mu I star times hi of x star should be equal to 0, and all these three conditions should hold for all indices I. That was the reason why we had so much space here on the right. You see how simple it is for the unconstrained case and how complicated it gets for the equality constraint case. There was one really useful thing, there are lots of useful things about the first order necessary conditions, but one thing is really helping us a lot in convex optimization, namely that they are also sufficient for convex optimization. They are sufficient. So they are also sufficient. That means that in convex optimization, I make here the brackets, we would have here an equivalence. So it's an optimizer if and only if this condition holds. And then we are done. If we know the problem is convex, everything is answered once you have found a KKT point. So these are called the complementarity conditions. So let me just remember that, and the whole thing together we call the KKT conditions, Karush-Kuhn-Tucker conditions. So now let's go on. Let's go on with necessary and sufficient conditions. Let's do them a bit separately. Second order necessary conditions. Necessary conditions are still of this form: x star is an optimizer, and that implies something. And what will it imply? It will imply something on the second derivative. For the unconstrained case, it's just that at this optimal point you will have positive semi-definite Hessian matrix. What will it imply on the equality constraint case? There are different ways to state it, but one way to state it is to say that we want to have the second derivative of the Lagrangian at x star and lambda star and mu star. So we need these multipliers already. These are also necessary conditions, so we know already that they exist. Sorry, there is no mu. And that this Hessian matrix is positive definite or semi-definite, but on a reduced space, namely on a space that we could represent by a basis Z. And this matrix should be positive semi-definite with Z, a basis of the null space of the Jacobian of the constraints dg dx at the point x star. I think we need even the next blackboard, so I will use some more space. I can also have an alternative way of expressing it. I could also say, in this case, actually, this Z spans the tangent space because of LICQ. So we could also say, for all P element in the tangent space of X star, we have the property that P transpose the second derivative of the Lagrangian at the right argument should be positive. Semi-definite, that means actually that the product of P times this Hessian times P should be positive for all P that are in the tangent space. And yeah, please remember that this tangent space T omega X star is of course the span of the metric Z. Okay, so this was still easy. But then comes again this very complicated vehicle due to the inequality constraints. And so here the condition is that we lend this notation, but it cannot be the full tangent cone, because there are some directions in which when we move there, we will have already first order optimality violated, so to say. And so in that sense, we just restrict our directions to all P in what we call the critical cone, and the critical cone depends on X star and on mu star, so it depends also on the active constraints, and we define it in a minute, but for all these it should hold that P transpose times the second derivative of the Lagrangian with respect to X at the optimal point X star, lambda star, mu star is positive or equal to 0. Of course, let's define what is the thank you. I'm just getting tired. Sorry. What is the critical cone? Thank you. So the critical cone was a subset of the tangent cone, and maybe I should define the tangent cone here as well. Maybe I just say it, then I have all definitions in one page. So it's the set of all directions which are in the tangent cone, which have this additional property that for all mu I star, which are strictly positive, you want actually that the gradient of this constraint at the respective point times P is strictly equal to 0. So actually it's a subset of the tangent cone, and the tangent cone itself, let's also define it because we also need it at some point. It's just all the vectors P, so that nabla G X star transpose P is equal to 0, and for all Hi of X star that are equal to 0, namely for all active constraints, we will have that nabla Hi of X star transpose times P is bigger than 0. So these are the directions in which we are allowed to move, while here we fix some of the directions, namely those that have a positive multiplier. Please note that you can only have a positive multiplier if the H is 0. So it's only, this is anyway a subset of the active constraints, and these are the strictly active constraints. So here we have the strictly active constraints, and here we have the active constraints. Okay, that is getting tedious, right? So easy, still reasonable, and then so complicated. But that's what inequalities do. And I want to go on, and unfortunately my table didn't give me enough space, so I will just prolong the table, because I also wanted to go into the second order sufficient conditions. So what do second order sufficient conditions do? They actually say X star is an optimizer, is implied by something. And it will be implied by some conditions which look a bit similar. So let me just make this table again. If there are questions, you can just ask them. But here it's unconstrained. Here it's equality, and here it's equality and inequality. And let's go on. So I think I need to move it a bit down. So then the second order sufficient conditions, X star is an optimizer, is implied by what? So what are the sufficient conditions that we need to know in order to be sure that something is an optimizer? We need to know, of course, first of all, it should be a stationary point. So the gradient of X star should be 0, and also its Hessian should be positive definite. So it's now positive definite and not positive semi-definite, so it's strict, all eigenvalues strictly bigger than 0. So these are the two conditions, and I connect them with an AND. So if these two things hold, then it's an optimizer. So for equality constraint optimization, these conditions are like before. It's actually nabla of the Lagrangian at X star, and there must exist a lambda star which satisfies these things. This thing, and also Z transpose second derivative of L X star lambda star Z positive definite, strictly positive definite. So these are the three conditions that we need for equality constraint optimization. And now for equality and inequality conditions, I will not repeat all the KKT conditions. Yeah? So the first thing is there must exist lambda star and mu star so that KKT conditions are satisfied. Yeah? So if you have found a point which satisfies these KKT conditions, and for all P that are in this critical cone, but which are not 0, you want that P transpose the second derivative of the Lagrangian at X star mu star lambda star mu star times P is strictly bigger than 0. I think that's it already. So these are the sufficient conditions for optimality. Second order sufficient conditions, as we abbreviate that. And there's one interesting thing that I stress very often, and that is something that I want to add here below the table. Actually, I can even add it here. You have, in the case that you have the second order sufficient conditions, you have also stability of solutions, stability under perturbations. And to be honest, the case where we really proved stability and differential dependence was in the case of strict complementarity. Yeah, so in this case, strict complementarity and second order sufficient conditions. Here there is no problem, actually, and LICQ should of course also hold. LICQ. Maybe I do it differently. I think I have a nice way to present it. We just say X star stable under perturbations. And in this unconstrained case, it's just implied by So this thing is implied by the second order sufficient conditions, so like that, right? And here it's also the second order sufficient conditions, but in addition we had this extra assumption which was LICQ, which I make explicit now, and for the equality and inequality constraint case we added to these assumptions also strict complementarity, because if we have weakly active constraints, the solution will not depend differentiably on the parameters. There was one interesting interpretation after we did this sensitivity analysis, and for the multipliers we could get an interesting understanding, namely we can interpret them as shadow prices. So we interestingly could compute actually the sensitivity of the optimal value with respect to changes in the constraints, and that is given by the multipliers. Okay, so in which chapters of the Nosedal book you would find these things? That would be maybe I don't move too often, right? So I say this is all in the Nosedal book. You find it in chapters 5 and 12. In this course we have decided to separate the exposition of the equality constraint problems rather than do it all together, because I think there's enough difficulty already here, and then the step 2 here is maybe less steep. So we also introduced one interesting class of optimization problems that is occurring a lot in applications, and these are the estimation problems. And I don't know if I really introduced it. Did I explain this? For me it's a highlight, so let me just say. In chapter 6 we talked about estimation problems, and one interesting origin of estimation problems is that when you have these least squares problems, so what are least squares problems? They are problems where we want to basically minimize the sum of deviations of some model outputs and compare them with measurements, and then we divide this thing with by some scaling factor that we call sigma I, and we sum over all possible measurements, maybe m. So we have such problems, and these are least squares problems, and they actually, so the argument that minimizes this is equal to a maximum likelihood estimate. So it's something that people in statistics like and find a good estimate. It's a maximum likelihood estimate assuming Gaussian noise. With variance or with standard deviation sigma I. So that's basically the assumption, or I can also write it like this. Eta I is then distributed according to a normal distribution which has the value of xi and the sigma I as the variance sigma I squared. So that's an interesting relation, and that was at the origin of least squares problems. And then there was also an algorithm, or there were some algorithms for linear least squares. Linear least squares, we could actually compute this using the pseudo-inverse. So the pseudo-inverse was a very interesting and important matrix, which was was also defined in the case of underdetermined problems. It uses what we call the SVD, the singular value decomposition, and it solves every well-determined problem, but it also solves the ill-determined problems. And then for nonlinear least squares, there were all these Gauss-Newton methods that we typically use, and there is, of course, Gauss-Newton is just for the unconstrained case, and once you get constraints into the boat, you call it generalized Gauss-Newton. So these are the things that I think are most important to remember about the estimation chapter. Yeah, and now I think it's maybe a good time for a short break, because now we finished the part on definitions and optimality conditions and theory, so to say, and we go into the algorithmic components. So how do we actually solve things? So that's what I will do after the break, but please digest what we did until now. It was, I think, already a summary of maybe half of the course. I want to continue our tour de force through the semester. What we will now do is look at algorithms, and I want to summarize 4 chapters in a quick way, and it's all about Newton-type algorithms. And this summarizes chapters 7, 8, 11, and 12. And in the Nosedal book, this could be found in chapter 2, this main thing, and then 6, 16, and 18. So what does Newton-type optimization generally do? It just iterates generally as it's an iterative method which goes into a direction which we call P, and sometimes this direction is dampened with a step that we call TK. Could be there or could be not there. And what this PK does, it's minimizing a quadratic model of our optimization problem, and this quadratic model could be a model that is actually this thing, mk of x plus p at xk plus pk is actually the function of at the current iterate, the objective function, the gradient times p plus a second order approximation which uses Hessian matrix. And what I wrote down is the unconstrained case. And if we want to extend it to the constrained case, then we have a QP. And then this QP is actually a bit more complicated, as we would assume. It's in the variable Rn. P in Rn, and it has, of course, this constant term, but I drop it because it's not so important for the optimizer, right? I still have the objective gradient. I have this approximation of my second derivative with this b, and then I have constraints in my QP, which are linearized versions of my equalities and of my inequalities. And this QP is then a quadratic approximation of my problem. No, it's not just of the function, but of the problem. And this is in SQP methods, sequential convex programming methods, for constrained optimization. So this is the big picture. So we solve somehow a quadratic model. It could be just a quadratic expansion of our function, or it could be a quadratic expansion of our function and also of the constraints. And then there is, of course, a crucial choice where this BK is the Hessian matrix. So you can have different choices for B. And we looked at several of them for what we call the Hessian. So the Hessian BK. Also, correctly, it would be a Hessian approximation. And one possibility is that we just say BK is a unit matrix. It's a very simple choice. It will lead to basically a kind of gradient method. And what convergence rate will it have? It's typically having slow linear convergence. So I say slow, this depends of course on the scaling of your problem, and there's exceptions to it, but typically it is slow. There's another extreme choice, that is to take the second derivative of the Lagrangian matrix at the currently best iterate. You also need some multipliers for that. We have discussed that. But how do you call this method then? You call it either the exact Newton's method, so the Newton's method, or you can also call it the exact Hessian SQP. What convergence rate will it have? It will have quadratic convergence rate. It's very fast and very nice, but you need the second derivative with respect to x, and this might even be indefinite, and then you get problems with solving your QPs. There's one several other choices. I want to go on actually with the interesting choices that you can do if your objective function has this, for some reason it has the property that it's just the square of some residuals, like we had in estimation problems. And if we have this case, we keep everything intact, but we just choose a special Hessian, and that is BK being equal to J of xk transpose J of xk, where J of x is the Jacobian of x, of R with respect to x. And this would be Gauss-Newton. And there's a related method that is, maybe I just don't, I could also add to this a unit matrix, a multiple of the unit matrix, and then I call the sole method Levenberg-Marquardt. Okay, I think with a T, I forgot the details. So this is a special choice, and it's only applicable if this condition is satisfied. But it has the advantage that this matrix is always positive definite. And what convergence rate will this method have? It will have good linear convergence. So it depends a bit on the problem, and we discussed the properties. If your functions are nearly linear, it will be very fast, and if the residuals are very small, it will also be very fast, but otherwise it can also be slow. There was another way to approximate the Hessians, and this was also that we could get the BK via updates. And this is something we can always do. It's not depending on the objective. It's another option. And this BK via updates is something which we also call quasi-Newton methods. And they typically have what we call superlinear convergence, which we also defined, right? And how do they work? They somehow require always one condition, which we call the secant condition. The secant condition is a condition that basically is something that the second derivative would also satisfy, or approximately satisfy. So we want that a new estimate of our BK, of this Hessian matrix, satisfies the property that the xk plus 1 minus xk, if we multiply it with the step that we just did, then it should be equal to the difference in the Lagrange gradients between the 2 points. And so these are the Lagrange gradients with respect to x, of course. And here we evaluate the Lagrange gradient at xk and then lambda k plus 1 and mu k plus 1. So this is what we call the secant condition. And to abbreviate things, we might call this sk and this whole thing yk, because then we can easier write down the following formula. And so you require the secant condition, and in addition, you require that bk plus 1 should be similar to bk. It's the other thing that we would like to require. bk similar to bk plus 1. And one example for this is the BFGS method. And that's the most famous one and most often used. BFGS update. And the formula for this is bk plus 1 is given by bk, and then there is a plus and a minus term, and the minus term is some symmetric matrix of rank 1. This expression here, and then there's a plus term which is also symmetric matrix of rank 1. I hope I got it right. Yes, I have. And one thing one can easily verify is that this satisfies the secant condition. And the other thing that you see immediately is that this is a rank 2 change of the original matrix. So it's actually not changing a lot in a high dimensional matrix, because this is a vector, this is the same vector transpose. Here you have also vector transpose. So this is a rank 1 matrix, this is a rank 1 matrix, and it's a rank 2 update. For this reason. There was a little lemma that is also something useful that I want to mention here, because it's a property that contributes to the success of the BFGS method, and that is that bk plus 1 is positive definite, or remains positive definite, and that is implied by bk positive definite, of course. You start with a positive definite matrix, but then also if your yk transpose sk is bigger than 0. So if this property holds, then one can show that the bk plus 1 is also positive definite, and that means that you have an easy way to ensure that you keep positive definite matrices. You start with a positive definite one, and then you check that this condition is satisfied. And if it's not satisfied, you modify your y in a way that it is satisfied. Okay. This was the first part of the summary. We also introduced some method that we called interior point methods, which I also wanted to introduce briefly. Interior point methods. They were a general approach to deal with inequalities. And I think in the Nosedal book you will find it in chapter 19. And in some sense what we solve is we solve perturbed KKT conditions. That's what we should think of, and we just recalled the KKT conditions. So what would be the perturbed KKT conditions that we solve for? It is this condition where we say the Lagrange gradient with respect to x, lambda and mu should be equal to 0, the equalities should be equal to 0, and the inequalities multiplied with the multipliers should be equal to tau for I from 1 to cube. So we replace these non-smooth complementarity conditions with a smooth approximation. That's a perturbation, and if the tau is equal to 0, if the tau is tending to 0, then we tend towards the right solution. And let tau go to 0. So that's roughly speaking the idea. You start with a big tau and then you make it smaller. And interestingly, these are the same, these are the KKT conditions. of a specific problem, which is a problem where we would have only equality constraints and where our inequality constraints would be moved to an objective. And so these are the KKT conditions of a barrier problem. We have derived that. And this barrier problem is the problem of minimizing x, where our function is f of x minus tau times the sum of the logarithms of hi of x 1 to q, subject to g of x equals 0. So if you solve this problem, and you have found a solution, then these are the necessary optimality conditions for that problem, actually, in a high-dimensional space. Please keep in mind that you use, of course, Newton's method, and you need warm starting all the time. So you need to start at the solution that you just computed, and that's the trick of the method. Without that warm starting, it wouldn't work. Okay. We also had discussed one important detail of all these Newton-type methods, and that detail is called globalization. Globalization was covered in chapter 9. Globalization was the property that you could start an algorithm anywhere and it would go to a local minimum. Yeah? Don't confuse it with global optimization. Just making it global that you can start anywhere, so to say. And in the Nocedal book, we find that in chapter 3.1 and 4.1, as far as I remember. And there are different ways to do globalization, and one was what we called line search. And here the basic idea was that we use xk plus 1 being the old xk plus some step length times the step that we get from our QP subproblem or from our linear solver. And then we need to have some things. So first of all, we need a merit function, at least when we have constraints. We had this T1 merit function, which was the objective, plus a sum of all the constraints, each of them penalized if it's getting violated, and then multiplied with some factors that we could call sigma I. And we do the same for the inequality constraints, where we take the, I like to write it like this. It's actually the negative part of h, so if it's negative, and then multiplied with some factors that we could call, maybe I call them tau I, h minus I. H minus is actually the violation of this thing. So whenever it's negative, you get a penalty, and if it's positive, you don't get a penalty. So this could be one interesting merit function. So you need the merit function. The second ingredient we needed for a line search was the Amio condition. So that's something that we needed always. And what did the Amio condition say? It said that your merit function at the new point, which is xk plus tk plus pk, should be smaller than the merit function, I call it t1, at the old point, minus, and then you take a factor gamma times tk times the directional derivative that your function has in the direction where you just computed your step. We express it in this form, so that's the directional derivative in the direction of p. And you want, of course, to go down, so this directional derivative will be a negative number, but just to make it clear that it's going down, I made the modulus here and I put a minus sign here. And gamma, you typically choose between 0 and 1/2. So you don't choose it too high. If you would choose 1, then this would be corresponding to the Taylor series, and you're not sure that you will find a finite value. And then a third ingredient for a successful line search algorithm was, for example, the backtracking, where you just backtrack until you have found a point that satisfies the Amir condition. Of course, there are different ways to compute line searches, which we mentioned, like the Wolfe conditions and so on, that don't need backtracking. But this was a simple and easy to implement nice algorithm. The second way to, maybe I still make the place here so that we see that it's in line. The second way to globalize was based on trust region methods. And the trust region methods, they were characterized by adding a constraint to our subproblem. So the main idea was that we add a constraint that our subproblem solution will not move too far away from the current point. So we add a constraint, namely that the P should be smaller than some delta K in a suitable norm. Could be the and we add this constraint to the QP subproblem. I don't know if I gave that name to that problem, so let me give this name. Here we have the QP subproblem. So we add this extra constraint. We have an unconstrained case, it's particularly easy, just add a constraint, and in the other case, you might get some problems if you get infeasibility of this problem, and then you need to deal with it, but these are details I don't want to treat, and we didn't treat actually. But you choose the trust region radius, delta K, so you make it bigger if you have a very good model, and you make it smaller if your model is not so good, and you know that when you make it small enough, your model in the neighborhood of this trust region will become good because you have all the derivatives evaluated. You have all the first order derivatives, and you choose it depending on some quantity that is actually the reduction of your objective function compared to the model reduction. At the new point. So you compare the actual reduction with a predicted reduction. And if that is close to 1, then you think you have a good model, and if it's close to 0, then you didn't really have descent. So this was the decision criterion here for sizing the trust region radius. This was it, what I wanted to say about globalization. It was very quick. And I want to go on with some other chapter that we did, and we actually talked a lot about derivatives, and then we used them a lot. So chapter 10 was about derivatives. I wrote them down already. Now again, like always, we write derivatives, but when we actually want to compute them, that's also a special science. And in the Nosedal you find that on chapter 8. And you remember there are some ways, symbolic, hand, that could be ways you can always do. There is also numerical finite differences, and that's something I think we should know about, finite differences. So how do we get some approximation of a function? If we take, so to say, the of any function, so given you have a function from Rn to Rm, how do we get an approximation of the Jacobian in a direction of one of its in one perturbation direction? Then we can get that by evaluating our function at a point xk plus some epsilon times p, x plus p minus fx, and we divide that again by epsilon. where epsilon would be approximately equal to or we could choose it to be the tolerance, the square root of the machine precision. So that is a very fast and easy way to get derivatives. And it has a bounded cost also. I mean, you just need to call your function twice. Or if you have several directions, then you can fix this point, you evaluate it once, and then in every direction you call this f again and again. So for computing the whole Jacobian, you will need n plus 1 function evaluations. So that's already a good thing. So the cost of getting the Jacobian, the whole Jacobian, nabla f, is equal to n plus 1 times the cost of calling your function f. This is in contrast to symbolic, where this cost could be outrageous if you just have wrong or big numerical symbolic expressions coming up. There's a simple way that we call the imaginary trick. I will not repeat it here, or I can actually maybe. It's just to use this same expression, but with perturbing into an imaginary direction. No, I will not record it. We explained it, and it's sometimes useful, but it's only applicable if you have functions where you can actually change from real to complex numbers easily. And then there is this field of automatic differentiation or algorithmic differentiation. And the abbreviation is AD, and that is a big community of people that develop tools that compute derivatives of computer functions. And the most important difference that we should keep in mind is that there is a forward mode, and there is another mode that is called reverse AD or backward AD. And what are the interesting things here? You have for the forward mode the cost of computing the whole gradient or the whole Jacobian of f is approximately 2n plus 1. If I have this plus 1 here of the cost of f. So 2 is slightly more expensive, right? Because but it's also more accurate. And for reverse AD, the cost to get the whole Jacobian is equal to about 4 or 3 to 4. What did I write in the script? 4 or 3? You don't remember? I don't remember, so let's be safe and write 4. And it will be m times the cost of f. So it depends now on the number of outputs and not on the number of inputs anymore, and that's exciting. There is one important thing here. You need to take into account memory. So reverse AD does a beautiful trick. It gets possibly very cheap, but it needs memory because it needs to memorize intermediate value in the function. And I just want to make some connection. There is in the field of neural nets, this is connected to what is called backpropagation. It's the same actually, just has a different name in a different community. And there is also an optimal control, and we mentioned that briefly. There is what we could call a backward sweep, and this backward sweep is also giving us basically reverse AD. I mentioned that we can eliminate multipliers, and this was actually similar to this reverse AD. And that's already a good keyword. Let's go to the last chapter that we did on optimal control. And the point that I wanted to make and to outline to you is that optimal control problems are nothing else than a specially structured form of an NLP. And we just state problems where we say that we have some states x and some controls u. They are actually time dependent, so they will be composed out of subvectors. And our main constraint that we always have is that xi plus 1 is equal to some function f of xi and ui. and xi and ui are vectors themselves. And this constraint holds for all system stages, so for all time points, from 0 to n minus 1. We also have an objective that is a sum from 0 to n minus 1 of some terms that depend also on these states and controls. And it might also be that we have a terminal cost that depends on, on the last state only, xn. And we might have more constraints. For example, we could have inequalities which are like these things, xi and ui could be positive for all the same indices. But we could also have boundary conditions, and we mentioned that there could be a boundary function x0 and xn that should be put to 0. And then we just say this is an optimization problem. It could be brought, and we did that, into the form of the general NLP, and then you can form the Lagrangian, you can differentiate the Lagrangian to get the necessary optimality conditions, and it will be very tedious because you will have a lot of different indices and so on, but you can do it, and it can help you to derive interesting algorithms. And some of the algorithms we derived were these elimination algorithms where you just eliminate a lot of things very quickly. Yeah, I think I will not rehearse the tips and tricks. We will have the opportunity to go deeper into these tips and tricks when we have the project presentations. But I want to outline one thing, which is there are two things actually, which I think I should still mention. The first thing is we will meet, or many of us will meet at a written exam. And so the written exam is at a certain date, which I forgot. Does any of the engineers know the date?
Middle of March.
Sorry?
15th.
15th of March, okay. It's morning or afternoon? Anyway.
Actually, the next day it stated that it's
okay.
oral exam.
No, it's a written exam.
It has the whole thing reserved.
Okay. Good, I will find out how to organize it, but it will be a written exam. And this written exam will be basically closed book, so I don't want to have people bring scripts and so on, but a paper, maybe two papers with 4 sheets, 4 pages, sorry, 2 sheets with 4 pages. That would be okay if you want to bring something. That's nearly enough to carry the summary. I will also put a sample exam from previous years online so that you get a bit of an idea of how these things look like. And some of the mathematicians prefer to, or not prefer, that's what in this faculty happens, is that you get oral exams. So we make individual dates then, and it has the same. So I wouldn't want you to always look up things in the script, but it's a talking exam. So that's what I wanted to say about exams. The next things I wanted to announce is that there is also follow-up possibilities for using optimization knowledge. So the first thing, and they will appear on the web very soon, but I already want to announce them so that I use the opportunity that you know about them. So one is that we want to have a seminar in this summer semester 2016, and this seminar will be called Model Predictive Control, and it uses a lot of optimization. It will be weekly meetings, 3-hour slots. They are a bit longer, but we will also have time for interaction in these slots. And at the first part of the semester, we will read papers, or different people will read different papers and present them to all of us. Yeah? In the second part of the semester, each person will work on a model predictive control simulation study, which is a bit similar to these projects. But it's about model predictive control, so it's solving optimal control problems of different sorts. It's a bit related. One of the projects is already doing this, I think. So it's in this direction. There's another thing, that's a seminar. Seminar and project. There is also a summer school. And that is, unfortunately, it's the first week of the holiday, so to say. Yeah, so that's the summer school. And the summer school is about optimization software. So we get an American guest professor. He will introduce people, or all of us, into different tools for optimization and comparison studies. And we will also do hands-on exercise on using different environments for optimization. Yeah?
Do you know the exact date?
Yes, it's the first week of the semester, as I said, so if you can extrapolate that and tell me, then I will write down. The first week of the holidays. It's something like the last week of July, I think.
It's a 2-week course, yeah?
It's we shortened it to only 1 week. It's a 1-week course.
1-week course. What are the 3 credits?
This will be probably 6, and this might be 3. Maybe it's only 1 week.
Yeah.
So we need to see how many credits we can give for it. Mm-hmm.
The semester ends on the 21st.
Okay, so then it's 22nd, 23rd.
On the 23rd, the Saturday, it will end.
Okay, yeah.
25th is the first Monday.
Yeah. And it's 20 up to 30. It's easy. No, it's even up to 29 only, right? That should be plus 1, yeah. It's 5 days.
Yeah.
Good. So these are the 2 things. The numerical optimal control school next week, I announced already enough, right? So I don't announce it again. You had the chance if you wanted. Okay. That's everything I wanted to say. Are there more questions? Yep. Sorry, here? 3. I said 3. Yeah. The point is 3 to 4. It's okay. I don't care exactly about the numbers. The point is it depends on what are your elementary operations, and so it can be a bit more expensive than forward mode.
Can you revise what you meant with the 2 points downstairs?
These things? Yeah? Okay, that was a relation to other fields. If you work with neural networks, people have an algorithm that's called backpropagation. Backpropagation. And it's a way how to train neural networks, and they are actually trained by minimizing a function. And in order to find the gradient in which you minimize, they use an algorithm that they call backpropagation, but it's basically a gradient computation using reverse AD. And in optimal control, there is a technology that you can call a backward sweep, where you first simulate your system and then you simulate some multipliers backwards, and that is something that we derived very briefly, I admit, but which gives you also the whole gradient of the objective with respect to all the constraints, and which can be interpreted, both of them can be just interpreted as just applying reverse AD to a complicated function which consists of concatenations of lots of things. Mm-hmm. And I mean, there's always back propagation, backward sweep, reverse. So whenever things go in the reverse flow of operations through a long computer function, then there's at least, so then you might suspect that there is reverse AD at work. And in these 2 cases it is. Yeah?
I have a question concerning the exam. How relevant are the proofs of the different parts?
Not so relevant. Yeah. So you don't have to repeat proofs. Mm-hmm. Maybe some simple reasoning, and you should be aware of what is true and what is false in general. Yeah? And what is necessary. I mean, that's why we took care about this direction of implications and so on. Okay. So if you agree, we could stop today a bit earlier. Yeah? And I thank you. It was an agreeable semester, and I'm now looking forward actually to Friday, when I will just listen and enjoy the presentations of the projects. So tomorrow there will still be an exercise session, of course, and so you can check with Dimitris and me about last-minute changes. On Thursday we want to have the reports. The reports should be handed in a bit earlier, I mean a day earlier basically than the presentations, in order to leave some breathing time for you to present. Because the presentations should not perturb, not interfere with the reports. Okay, that's all. We will see again on Friday, here in this room.
The technical faculty at the same as the exercise? Or? No.
We are here in this room on Friday. Yeah, Friday we will be here in this room, and that's actually a good point. Do we have a projector in this room? Do you know about it? Yes, there is a projector. Good. Okay, so if you can, I would be happy if you bring your laptops for presentations. Yeah? Yes?
People ask whether we have an HDMI connection or not.
HDMI. It looks we don't have. At the moment, this is here.
It's that thing, one laptop where it's working and everyone plays a PDF.
Yeah, that's also possible that we just bring PDFs, but some people please bring also your laptop so that we have fun.
But to have a PDF on the stick.
Yeah, PDF on the stick is a good idea, or maybe PDF plus one video if you want to have a video. But if you want to give a demo in MATLAB, then it is... and we should actually discuss about the time. How long would one presentation be? Do we know how many we have? I forgot that. Did we? Yeah, how many groups? We had a Google Sheet for that, didn't we? But you don't know. Andrea, do you know how many groups we had? Yeah, you check it. So I guess that some duration close to 10 minutes would be appropriate.
Because on the sheet it was like 15, but it's too much for 1 hour for our groups.
Yeah, 15 minutes would be too long. Yeah, so we do 10-minute presentations, otherwise we get crazy.
Yeah.
Is 10 minutes good? So 10 minutes basically means 5 slides, not more. Less is always possible. Okay, but anyway, I think, Andrea, you didn't find the number, but I think with 10 minutes we are safe, and if we have 15 groups, then it would be 150 minutes. Let's aim for 8 minutes, okay? So, I think we don't have 15 groups. I think we have much less. I mean, we will see how many groups we will have, but prepare 8-minute presentations. Yeah? 8 minutes. 8-minute presentations, 4 slides basically. I mean, we also have the reports. Yeah, you can use material from the report for the slides if you want. Mm-hmm. Okay, thanks a lot, and see you on Friday latest.